Okay, so I guess we're going to start. It's a great pleasure to welcome to our J1 series of seminars to have our today's speaker, Klaus Leitherer. I thank him so much for actually, volunteering to give this talk, and especially this is a special day for the French, so 14th of July. So anyway, so Klaus Leitherer is an expert on stellar evolution and atmospheres with emphasis on massive stars, and he leads one of the major stellar population synthesis codes, Starburst 99, and its most recent version, Pi Starburst 99, that specializes on young populations in galaxies and systems with ongoing star formation. So our speaker works at the Space Telescope Science Institute in Baltimore in the USA and has served in a number of key positions involving science policy, the oversight of HST and James Webb proposal selection, and the management of the Hubble Fellowship Program. Dr. Leitherer did his PhD in Heidelberg, Germany, followed by several postdoctoral positions in Heidelberg, in Colorado, and at the Space Telescope Science Institute, where he joined as ESA staff astronomer, staying ever since. Closer to IAU, he also served in Division J, Galaxies and Cosmology, as president and advisor. And today's talk will focus on hot stars in the stellar populations of galaxies, a very timely topic with such a large number of excellent data of high redshift galaxies from James Webb. So Klaus, thanks so much for giving this talk, and take it away. Thank you.
All right. Thank you so much for the kind introduction. And despite the fact that I'm showing this very nice image from JWST on this lens cluster, I will actually start much closer to home, precisely at a distance of about 2 kiloparsecs. And what you see here is the area around the Carina Nebula, which includes some of the richest clusters we know in our galaxy, Trampler 14 and 16, which both host some of the most massive stars known in the galaxy. There's also Eta Carinae. It's the famous star that experienced a huge eruption in the 19th century. It's in the center. You can see this here. And there are other stars of note. For instance, there's HD 93129A, which is an O2 star, which is the earliest spectral type that is known that has been classified. Okay? And let's look at this in some more detail here. So this cluster is close enough to allow us to study individual stars in great detail. And here is a list census of the earliest types of the most massive stars in Trampler 14. You can analyze them, you can derive the luminosities, you can derive the ionizing luminosity output of hydrogen ionizing photons. Then you can compare this to the properties of the surrounding nebula, of the recombination flux, and you find that the nebula H alpha is about 70% of the stellar ionizing flux. Well, depending on your perspective, you could say, well, it basically disagrees. Now, if you really trust these numbers, you can speculate that either, say, maybe 30% of the stellar photons, UV photons, are absorbed by dust, or that they escape from the nebulosity without absorption. Then you can also look at the stellar winds of these stars, the mass loss rates, the velocity. You can calculate the kinetic energy that's injected in the surrounding nebulosities, which is about 30% of the stellar wind energy as measured from the emission lines, like from H alpha. Now I should say that these are young clusters, less than about 3 million years old. So basically the energy input by supernovae is most likely still negligible. Now, would it not be great if we could do the same game much further out? Well, let's look at some galaxies at larger distance. To the left, that's He-Nice 210. It's at a distance of about 10 megaparsecs. And the region we saw before, Trampler 14, 16, would be one of these blue little dots, completely unresolved. So what you see here, if you can see my cursor here, so these are not individual stars, but these are all clusters, each of them with masses of about 10 to the 4, 10 to the 5th solar masses. Now you can go even further out, and that's a very famous galaxy at high redshift goods north, Z11, and well, with the best data you can get, well, you still see this kind of plot. But we would still like to know actually what are the properties of these plots, what kind of stars are there, what are the properties of the interstellar medium. Well, and this is where stellar population synthesis comes into play. So the goal here is to model the spectrophotometric and other properties of stellar ensembles. And in principle, this is actually a very simple concept. There are several ingredients. You have to make an assumption on the star formation, which includes the initial mass function, star formation history, clustering, and so on and so on. Then everything related to stellar evolution, which basically converts a mass as given by the star formation law into a luminosity and introduce a time scale, how the luminosity changes as a function of time. And then, of course, you want to compare this to observations. So typically then you link this with spectral libraries, which can be empirical or theoretical. And then there are several other ingredients, dust, geometry, and so on and so on. Now here's a nice schematic, which was published by Charlie Conroy 12 years ago. And it shows you all these ingredients. Top left is essentially the star formation, the initial mass function. In the middle, then top middle, the stellar evolution models. It's a Hertzsprung-Russell diagram with isochrones. And then to the right is the stellar library. These are individual stars. So you can see when you have a hot star, an O5 star, you get lots of ultraviolet flux. When you get a late-type star, then the SED shifts into the near infrared. You put this together, and then you get an SED of a single stellar population. And depending on what your interest is, you can combine this with chemical evolution models. This shows you how the metallicity evolves as a function of time. And then, of course, galaxies are typically dusty. You would put in dust absorption or emission, and then you get your final SED. So if there's little dust, this would be the blue curve here. There essentially peaks in the optical or ultraviolet and drops off to the near infrared. Once you add dust, then the SED shifts to the mid and far infrared. And so typically with some dust, you have this kind of double hump, so that you have one peak in the far infrared and one peak in the optical ultraviolet. So that's what it looks like. So in principle, this sounds straightforward. And of course, there are quite a few public packages that do this kind of population synthesis. And here I have a list. I'm pretty sure I forgot somebody, and I apologize for that, but these are the ones I think I encounter most often in the literature, and they're here arranged in alphabetical order. Yeah? So this is just for the record. Okay. And so here are just a few examples of model predictions from Starburst 99. So these are 25 years old, but it just shows you the principle. So to the left, it shows you the SED, how it evolves over time. If you're young, you have lots of flux in the ultraviolet. Once you're older, then basically you would drop off, and the peak shifts to the near infrared. And this is without dust. So these are all single stellar populations, an instantaneous burst. So you can do, you can model the ultraviolet spectrum, which is here arranged as a function of age from 1 to 20 million years. You see strong stellar wind lines, and I will come to this later in more detail, which then drop off once the O stars actually die after about 10 million years. And so here's then predictions like the luminosity, the supernova rate, colors. Now, here's something that's probably of interest to this audience here. This is the beta slope. It's essentially the slope or the blueness of the ultraviolet SED, which is often used to infer the presence of massive stars and the dust reddening. It shows you that basically for the first 10, 20, 50 million years, essentially the UV slope, the spectral energy distribution, has an index of the order of -2 to -2.5, and with very little variation with stellar properties. It's only at older ages, then it would drop off rapidly once the OB stars are gone. This is the equivalent width in H alpha. Essentially, it shows you basically the age and of the starburst, and then you run out of ionizing photons because the hot massive stars are gone. And then finally, let me just show you this one here. This is the mass of the cluster. So these models refer to a single stellar population with mass of 10 to the 6 solar masses, and it shows you then how the mass decreases with time, and after 10 to the 9 years, if the cluster is still stable and alive, essentially most of the mass has been returned to the interstellar medium due to winds and to supernova explosions. So in principle, this looks all good. So how does this work in practice? So here I show you one example. So this was a recent paper we did with Daniel Berg in the lead. So this is spectroscopy of individual H2 regions and the ionizing star clusters in the nearby Grand Design spiral M101. And so the data set was a combination of HST ultraviolet spectra obtained with COS plus also optical data. And this allows us then to probe ages and abundances. And what's here, so this each of these sections is one giant H2 region, and I'm showing you only the ultraviolet spectrum, and they're arranged by increasing age. The youngest is up here, and the oldest is here. And what you see here is in black the data, and then in red and greenish there are two sets of models. One is Starburst 99, the other one is BPAS. BPAS are the models that have been developed in Auckland, led by John Eldridge. And the special feature of BPAS is that it includes binary stars, which is an important ingredient. Starburst 99 only uses single stars. And if you look at this very strong line, typically the strongest, it's the carbon-4 1550, you see almost perfect agreement. And you can basically fit the continuum, the lines, and the continuum slope to derive independently ages, metallicities, and also dust reddening. And you see this works actually quite well. So the other lines, there's the nitrogen 4 line, it's at 1720. There's a silicon 4 around 1400, and the fit is generally quite good. And I should say, so these models do not take into account interstellar absorption lines. What you see here is these very sharp lines. These are actually interstellar absorption lines, which are obviously not modeled by a stellar code. And yeah, so this is the ultraviolet, the far ultraviolet down to 1000 angstroms. So this is the oxygen 6 line here, and there you see the difference. There are two sets of models. One set of models includes X-rays, the other doesn't, and oxygen 6 actually is basically completely determined by the amount of X-rays in the stellar winds. If you do not include the X-rays, you would not be able to reproduce the line once you account for the X-rays, and again you get a reasonably good fit. All right, let's continue here. So after this relatively lengthy introduction, so I want to focus on 3 topics here, and I pick 3 topics. They're related to massive stars, and I think these are questions that are of interest to this particular audience. And so these are really hot topics where lots of focus actually right now is in the literature. And it's a search for very massive stars, then the hardness or softness of the ionizing spectra produced by these massive stars, and also the chemical enrichment of the interstellar medium that is produced by these massive stars. Okay, so let's start with very massive stars. And just to be clear, what I mean by very massive stars, these are stars with masses of at least 100 solar masses, if not 500 and possibly up to 1,000 solar masses. And the question is, do these beasts really exist? Okay. So what would they look like? So here is a figure which shows you spectra that were obtained with the Ulysses survey. This is a program, JWST Director's Discretionary Program, that produced the UV spectroscopic library of O and B stars, mostly in the large Magellanic Cloud and in the small Magellanic Cloud. And so there are several hundred stars which then actually are being used for forming a stellar library. Now, below there, these are stars in the LMC, and so these are the early type supergiants, and these are stars that are very massive. So possibly they would actually possibly reach the definition, maybe up to 100, but the defining feature is, for instance, that they have this very strong helium-2 line in emission. It's at 1640 angstrom, and also other emission lines. Now let's focus on one specific region, namely NGC 2070, which is essentially the ionizing cluster of Doradus in the LMC. And so this is from a very nice work by Paul Crowther and collaborator, where essentially took STIS, one of the spectrographs of HST, and basically took stepped long slit spectra across the center of NGC 2070. Remember, we don't have an IFU in the ultraviolet, and that essentially simulates an IFU. And then you get spectra of all these stars, and then you can put them together, and you also get the integrated spectrum of the center of NGC 2070. Okay. Now, this is the integrated spectrum. That's what it looks like. Now, since you know the spectra of the individual stars, you can show actually that basically the continuum comes from tens of maybe 50 or so stars which are in the central region, but some of the strongest emission lines, the helium-2 1640 here, or also the nitrogen-5 here, come exclusively from the very center called R136A. So this is a handful of stars, okay, which can then be studied individually. So we know actually that this line essentially comes from these individual stars. And now we can look at these stars in more detail. So these are now studies of these individual stars. And let's just look at the top left diagram. It's the Hertzsprung-Russell diagram. These stars have been analyzed and masses have been derived. So these are not binaries. So this has not been derived from binaries. It's an atmospheric analysis where you derive effective temperature and log G. And with some error bars, the masses of these stars are of the order, say, between 150 and 400 solar masses. So these are very massive stars. So we now know that in this integrated spectrum of R136, we have very massive stars, and we know what the telltale sign is, namely, for instance, the helium-2 1640 line, there's a nitrogen-4 at 1483 and other lines. So when we see these lines in other spectra, there's a good chance, the high likelihood, they're also very massive stars. Okay. Now we can compare our template spectra of R136, which is in the middle, so it's the third spectrum from the top or from the bottom. So it's the same spectrum as before, but binned to the same resolution of the galaxy spectra. And now this is compared to other regions, nearby dwarf galaxies, out to a galaxy at a redshift of, I think, 2.7, the sunburst cluster. Okay, and you can see the similarity of the spectrum here. So here's again the helium-2 2 line, then here's a nitrogen 4 line, and then there are other lines which indicate that these clusters or regions of galaxies also host very massive stars. Now let's look at this galaxy in somewhat more detail. This is NGC 3125. Okay, the spectrum you saw before actually refers to this region here, to this cluster. It's actually 2 clusters. Okay, so the galaxy itself is actually similar to the LMC in terms of the metallicity. It's about half solar. It's a distance of a little bit more than 10 megaparsec. And this cluster, NGC 3125A1, has a mass of the order of 10 to the 5th, or maybe even a little bit higher. So it's pretty massive, actually. Right? Okay. Now, some 10 years ago, Ida Wofford, who worked with me at that time, who was at Space Telescope as a postdoc, tried to model the spectrum of this cluster. The spectrum and the model is the top here. Black is the data, red is the model. And below that's the error spectrum. Ignore this. So it's only the top, and you can see overall it's a decent fit. There's the carbon 4 line, there's the silicon 4 line, there's nitrogen 5. However, there is a spectacular failure. There's a 1640. It's very, very strong in the spectrum, but the models at that time did not predict anything. So clearly the verdict here is something is wrong. Now, fast forward 10 years. So now AIDA tried this again. So this the black is the data, is the spectrum, and blue are the models. Now, look at the fit. Here's again the helium-2 line. Perfect fit. Also the other lines, the carbon 4 line, the nitrogen 5. So what has changed? Now there are models available for very massive stars. In this case, there are these very massive stars, so these are 300 solar mass stars, which have very strong winds. So these are these very strong stellar wind lines. So these are probably very similar to the stars we observe in the center of Doradus in R136. Once you add them to the models, then you can reproduce the data. Okay, so this was my first part, and this is the takeaway message here. And I read this to you. So there's strong evidence for the existence of very massive stars with masses of several hundred solar masses, both as individual stars and in unresolved star-forming regions of galaxies. Now let's move to the next part, namely the hardness or softness of the ionizing spectra. All right. In particular, at metal-poor galaxies and also at higher redshift, we very frequently observe highly ionized nebular species, like the carbon-4, now nebular carbon-4, 1550, also the helium-2, 1640. Now, this is not to be confused with the helium-2 we saw before. This is now a nebular line. It has nothing to do directly with stars, although it may be powered by stars. But these are now lines in the interstellar medium. It is sometimes observed in the local universe, but it's more the exception than the rule. But it's very frequent at higher redshift. And the question is, are stars the powering source? What's the origin of these lines? Just for reference, in order to account for nebular helium-2 1640, you need photons with an energy of at least 54 electron volts, which is quite a bit. All right. Now, well, in the previous section, I talked about these very massive stars, and these very massive stars are very luminous. So they sit in this part of the Hertzsprung-Russell diagram, and they're quite hot, right? So this is a Hertzsprung-Russell diagram recently published, compiled by Thomas Chenard, which shows basically all the relevant population in the upper Hertzsprung-Russell diagram in the large Magellaниc clouds. And they identified different classes of stars: red supergiants, yellow supergiants, blue supergiants, and then very massive Wolf-Rayet stars. Now it has become obvious in the past several years that Wolf-Rayet stars come in two flavors. One flavor sits here. This is what we call the classical Wolf-Rayet stars. The view has always been, well, Wolf-Rayet stars are basically the evolved descendants of O stars, where the core, the naked helium core, has been exposed. They're hot and they're essentially hydrogen free. But then there are also other Wolf-Rayet stars which look very, very similar in the spectral appearance, because they also have very high mass loss, and these are these stars here. They're classified as Wolf-Rayet stars, but in reality, from an evolution point of view, they are still O stars. They're still on the main sequence. They're core hydrogen burning, and they still have a significant fraction of hydrogen left. So spectroscopically, they look very similar. But once you do a detailed analysis, they're very different beasts. Okay? Now, since these stars are so hot, you can see actually they reach temperatures of 60,000 K. You might say, well, these stars should be able to account for the ionizing photons of these highly ionized spectral lines. Unfortunately, it's not so straightforward. These are spectral energy distributions of two massive hot stars. To the left, this is actually a model spectrum of a hot O2 star in a small Magellanic cloud. It has a luminosity of about 10 to the 6, an effective temperature of 51,000. To the right is a somewhat hotter and much more luminous star, which is close to 10 to the 7. So this would be one of these very massive stars, which sits at the top of the Hertzsprung-Russell diagram. So the SED here is color-coded, so lightly shaded. This is the non-ionizing ultraviolet, everything longward of 912 angstrom. This is the next one, is the hydrogen ionizing part. So that's everything between 912 and 504 angstrom. Next comes the neutral helium ionizing part from 504 down to 228 angstrom. And then finally, the red, the dark part, that's essentially the ionized helium part. So this is everything below 228 angstrom. So that's what you need actually, for instance, to account for the nebular helium-2 lines at 1640 or at 4686. Now, so this is the cooler star, this is the O star, and you see there is some output in helium ionizing photons. Okay. Now here actually what you do, you ramp up the temperature, you get many more hydrogen ionizing photons, almost an order of magnitude. But what happens here is, because of the high luminosity, there's a very dense winds, and the helium ionizing photons cannot leak out of the envelope anymore. They get absorbed in the star itself. So, and therefore, they are no longer there for the interstellar medium. So essentially, you get exactly the opposite of what you want. So these very massive stars are, in fact, not good candidates for ionizing the surrounding interstellar medium. Okay. Now, then let's look at these core helium burning Wolf-Rayet stars. So they're less luminous, obviously, so they're by an order of magnitude, but they're definitely hotter. Now, they have been suggested to be the source of the observed narrow helium-2, nebular helium-2 in the nearby dwarf starburst galaxy, entity 1569. So this one is a little bit less metal rich. And so Maya and collaborators, they compared the nebular narrow helium-2, the recombination line flux, to the population of Wolf-Rayet stars, classical Wolf-Rayet stars, and their conclusion was that these classical Wolf-Rayet stars, so these are not very massive stars, they in principle should be able to account for the photon budget above 54 electron volts. On the other hand, there are also counterexamples. There's another very famous galaxy, SPS 0005 052, studied by Carolina Carrick and collaborators. They actually, this game did not work. So they actually the Wolf-Rayet stars could not account for the observed recombination flux in helium-2. Now you can also do photonization models where you essentially use stellar population containing Wolf-Rayet stars and compare this to observations. In this case, this is work by Nell Byler, where she took a small sample of a 30 Lyman break galaxy with an iron abundance of about a 10th solar. So they had a redshift of 2.4. These are the data points. And so this is a grid of photonization models. The horizontal lines is the ionization parameter, and the vertical lines the metallicity. And you can see, for a certain age, when you hit the age range of 3 to 4 million years, then these models, 3 to 5 million years, then these models in principle can account for the ratio of the helium-2 1640 over H beta when plotted against O3 over O2. Of course, that requires a carefully fine-tuned age range, and it would really only work in this age range simply because these Wolf-Rayet stars have a very short lifetime, or only a few 100,000 years, and you only get this for a very, very short while. So it's not clear actually if this is true in general. So at this point, the situation is the models do not reproduce the highest ionization lines emitted by the ISM in these galaxies, even if very massive stars are included. This may mean that there are shortcomings in the models, or it means that we would need other ionization sources. Maybe there are shocks, AGN, or whatever. So, but at least with the models, we are not there. So we cannot really exclude that massive stars do not can in fact ionize the interstellar medium. We're just not quite there yet. This is still an open question, and it's really a very active field of research. And let me look at my time here. Yeah, I think I'm good. That brings me to the third section. It's the chemical enriched mass loss. Right. Okay, and let me focus here on the sunburst arc. It's a beautiful example of a lensed galaxy. It's up to a factor of 80. It's a galaxy at a redshift of 2.4, studied in great detail. And you can see there's the arc. You see these clusters. So actually, there are several clusters, but some of them are as one of the same cluster, multiply lens several times, which allows you then to basically to stack the spectra and get a optical ultraviolet spectrum of the highest quality. So essentially you get spectra which have a quality which actually exceed the quality of galaxies we can actually obtain locally. Okay. Now, so this also allows the measurement of nebular abundances using a direct method, meaning one can independently determine the electron temperature and the electron density. And so what you see here are abundance ratio. Horizontally here, that's the oxygen abundance, and there are various elements that have been measured. So there's a local comparison sample. So the galaxy, the sunburst arc is here. And I want to focus on nitrogen over oxygen, which is the top panel here. And you can see, so there's this very nice relation. It's very well known. At low metallicity, basically you have a constant N over O. because nitrogen is primary. Once you go to higher metallicity, then you also get secondary production and you get a dependence of NO on the oxygen abundance itself. Now, clearly, the NO is sticking out. It's enhanced by about 0.8 dex relative to H2 regions of similar O over H. And then you can look at the rest frame optical spectrum here. And in the spectrum, you can directly observe very massive stars, classical Wolf-Rayet stars as well, both of the nitrogen-rich and of the carbon-rich flavor. You can count those the Wolf-Rayet stars, and you find that there's a total of 700 Wolf-Rayet-like stars from a comparison with population synthesis models. And so the suggestion is that these Wolf-Rayet stars, which are highly nitrogen enriched and have strong solar winds, are the source of the nitrogen enrichment in this galaxy. Now let's go further out. So this was at a redshift of 2.4, just as a reminder. The age of the galaxy, basically this is cosmic noon, is about 2.2 gigayears. Now let's go to Goods North, C11, when the age of the universe was a little more than 400 million years. So it's a similar plot now. You can look at the nitrogen over oxygen ratio in this galaxy relative to the oxygen abundance, and you can see that there's a significant nitrogen overabundance in this galaxy, which the authors report to be a factor of several above what you would expect at this redshift. I should say, of course, you have to work with the data as you get them, so don't want to get into details here, but determining the nitrogen abundance in this with this data set, it's a heroic effort, and it's not done the standard way, although the authors give arguments that the result is in fact believable. And again, the suggestion here is that there are very massive stars that form actually in the centers due to of this very dense cluster, and then the nitrogen will be released either directly by winds or also via explosion in supernovae. Now this was nitrogen. Now, of course, what's particularly interesting is iron. Now, determining iron in hot stars, in old stars, that's something that is still beyond the current state of the art. While determining iron abundances in, say, late-type stars, well, that's an easy matter. You have neutral or singly ionized iron, and you get iron abundances. Now, in old stars, the dominant ionization stage is actually iron 4, iron 5, and iron 5 is complicated. So here's a Grotrian diagram of iron 5, and I think it doesn't need any words. Everybody would agree that this is very complicated, and modeling this in non-LTE for all the transitions, it's basically not yet doable. Okay, so work is underway, but it's just, we are not quite there yet. However, at least in integrated galaxy spectra, there's a workaround. So this has been used for at least the past 10 years. So essentially the line blanketing that you observe in the ultraviolet is due to millions of these faint iron 4, iron 5 lines. Okay? So this shows you theoretical UV spectra as a function of metallicity from supersolar to about 1/20th solar. And you can see actually that the blanketing, just the lines you see here, increase as expected with metallicity. And essentially you can use this blanketing to as an indicator of the metallicity. Now, the models are certainly not correct for each of these lines individually, but on average, the models give a reasonable prediction for the metallicity. Now, I should say um, this assumes a certain microturbulence velocity, because in individual stars, of course, there's an intrinsic broadening. The reason you can do this for stellar population spectrum, there you can hope that over thousands or tens of thousands of stars, you essentially take the average microturbulence velocity. In this case, what has been used is 10 kilometers per second. Now, if you do this for an individual star, then you would also have to know the microturbulence velocity, which can be 1 kilometer per second, can be 20 kilometers per second. But on average, it's about 10 kilometers per second. That's why this actually works for a stellar population. Okay? And so this has been done then for galaxies. So now this is a kind of busy plot here. So this is a stacked spectrum of a sample of Lyman break galaxies at a redshift of 2.4. And so if you can see this in black, these are the data. And then superposed are several models. And I want to direct your eye to the right part here. And what has been done now, essentially take the blanketing. So what you see here is also, this is a kind of, these are blends of many, many, many iron 4, iron 5, maybe also iron 3 lines. And then there's a comparison between the models of various metallicities with the data, and you can show actually that the iron abundance in this spectrum is of the order of 1/10 solar. At the same time, then one can use the nebular emission line, the ISM lines, to derive oxygen abundances. Now, when you derive the oxygen abundances, you find that the metallicity is actually much higher. So the oxygen abundance is about half solar. So there's a difference of a factor of 5 between the iron abundance and the oxygen abundance, meaning oxygen is enriched by a factor of 5 relative to the solar ratio. Okay, and this has now been done in other regions. So this is from work by Cullen and collaborators, where they studied the mass metallicity relation for the stars via iron and for the gas via oxygen at a redshift of 3.5. So the lower set of data plotted in blue, these are the iron abundances as a function of galaxy mass. These are the stellar masses of the galaxies, and these are compared to the oxygen abundances in the same galaxies. And again, you see that the oxygen abundances are higher by a factor of 2 or 5 or so. And the interpretation is that there's oxygen enrichment due to core collapse supernovae in these very strongly star-bursting galaxies. Okay? So, and what do I do here? Yeah. So this was my top takeaway in part C, namely, wanted to show that massive stars return chemically enriched material, nitrogen, oxygen, via powerful stellar winds or core collapse supernova explosions. Okay, so let me spend the last 5 minutes with a look into the future. What's next? Of course, mentioned already, Starburst 99 has been around for a while. But now there is a new release of Starburst 99, thanks to my postdoc, Callum Howcroft. So the paper has just been out. It's in the archive, and it should any week now show up also in the journal in AppJ supplement. And so it's a new version. And in terms of physics, it now includes models for the most massive stars, now going up to 500 solar masses, all taken from the Geneva set of evolutionary tracks. We also now have a much larger range of stellar metallicity, which goes from twice solar, and then it covers solar, LMC-like, SMC-like, 1/30th solar, which is like the famous 1/18, and also zero metallicity. Okay, and this is both for rotating and non-rotating stars. And to the left is just one example for some of these very massive stars. We also have a new set of model atmospheres, much more extensive, and we are still working on implementing the empirical Ulysses spectral library. I should also say that the original Starburst 99 was written in good old Fortran, but now being the 21st century, the new version is actually in Python, although we still have a version in Fortran, but the new version is in Python. Well, it was actually funny when we submitted the paper. So the referee found this actually as a negative that the new version is in Python. So the referee would have preferred to stick to Fortran. Well, yeah, can't satisfy everybody. Anyway, so let me just show you just a few results, and I encourage you to go to the paper, which is in the archive. So this just shows you the ionizing fluxes that with the new models. So adding very massive stars essentially doubles the hydrogen ionizing photon output. And when you look at very metal poor populations, owing to the behavior of the stellar evolutionary tracks, you actually get still a very hard spectrum at older ages, up to 10 million years. Okay, so overall you increase the ionizing photon output. Also the wind momentum, the input of momentum, and mechanical luminosity increases by a factor of several when you include these very, very massive stars, simply because their mass loss rates are so much higher than for less massive stars. Yeah, so these models will be available, so stay tuned. And of course, there are objects waiting to be analyzed. So here's an example. So this is another record holder, at least it was when it was published, galaxy at a redshift of 12.3. So the age of the universe was a little bit less than 400 million years. It's a JWST prism spectrum. So this is a very dense cluster where you basically have 10 to the 4 solar masses with concentrated in a parsec or so, and with a very, very high ionization parameter. And so these are some of these galaxies we hope to model with Pi, Starburst 99, or with other population synthesis code. And I leave it with this nice spectrum and here, and I'm happy to take questions.
Okay, thanks so much, Klaus. Very, very nice talk. Lots of very interesting results, and yeah, looking forward to seeing the Starburst 99 new models. So now we opened it.
Should I stop sharing or should I leave it?
Maybe you can keep it like that. I mean, I will just I will just make this a bit bigger. And so for those of you who want to ask a question, please, I guess you can simply turn on your camera and ask a question. In the meantime, I was wondering, Klaus, you were not mentioning, you referred to BPAS, but here you were not mentioning this. So regarding the effect of very massive stars, what is the role that you could think of in terms of binarity? Because in principle, massive stars will have a large fraction in principle of binaries. Could that be a source of degeneracy somehow in some of these results?
Of course, these very massive stars also have a very short lifetime, right? So they only live for about 2 to 3 million years. So and typically the binary interaction only sets in at older ages. It takes a while, so it's not so clear, right? what's going to happen. Um, this has not yet been explored, but just giving this hand waving argument. But clearly, once you go to older ages, binaries are very, very important, right? In particular, if you want to account for this very uh, hard ionization which you observe in some galaxies. So as I said, the very massive stars certainly don't do the trick. In fact, it's just the opposite what they do because they use up the photons in the stars themselves.
Yeah. And in the formation process, you would envision that these very massive stars would form in the beginning, or it would take just a while. I mean, what would be the hierarchy in the formation?
Um, well, there's if you look at 30 Dorados, right? I mean, they seem to be forming at the same time. They are there together with the somewhat less massive stars, at least in this region.
Right. Um, so, please go ahead. Yeah, so Ralph.
I was wondering, Klaus, is there a fundamental limit to the upper limit to the mass of massive, these supermassive stars? You put 500 solar masses and also to the luminosity?
You mean in terms of the star formation and stability?
Yeah, for example, yeah. What do you think would be the most massive one which could exist?
Well, of course, then there are models for primordial, completely metal-free stars. And there are models for extremely massive stars with 10,000 solar masses, right? Now, if they exist, that's a second question, but they have been postulated to be the source of reionization of the photons, basically for the first generation of stars. Now, observationally, what we believe are confirmed masses, they are of the order of a few hundred. Now, if you want to be really conservative, then you could say, well, what are the most massive stars where the mass has been confirmed from a binary itself, from an orbit? And there the most massive stars are around 100. Incidentally, there was a very nice paper in the archive just a couple of days ago by Phil Massey, who actually reviewed the topic. So I recommend this. So the situation is confirmed stars with binary orbits is about 100, and there are few actually. Then confirmed stars from a model atmosphere analysis up to, say, 400 with some error bars. And more massive than that, that's basically subject to speculation.
Okay, thanks a lot.
I mean, in this area, so comparing the presence of very massive stars, because you have considered, for instance, like the LMC R136, which would be a lower metallicity type of environment, and the type of data that we get in James Webb, which in principle, if those are the ongoing sites of galaxies that eventually are very massive, in principle, you can build up metallicity quite strongly. So, what do you think would be the role of metallicity in whether these very massive stars are present or are important or not?
Well, that's actually some subject to current research. So what we have, so the galaxies I showed this montage of 5 spectra where we believe there's indication of massive stars. So they cover the metallicity range, say oxygen abundance, from LMC down to close to 1/10. And there doesn't seem to be, of course, it's a statistics of 5 or so, right? So in principle, there is no strong metallicity dependence. I mean, the Wolf-Rayet star they form actually also at lower metallicity, possibly via binary interaction. That's actually where binaries become very important. So in principle, of course, if you have only single stars, it becomes very, very difficult actually to form Wolf-Rayet stars at very low metallicity. Now, once you have binaries, then you basically remove the material, the surface layers via gravity, and gravity doesn't care about metallicity.
Right. Okay, thank you. Any other questions? But just brief one, and excuse my ignorance on this, but I was wondering, another source for basically you're trying to explain this helium-2 line. I could imagine that there is no way to do this mechanically, like shocks cannot produce this. I mean, could you invoke those to explain the mission that you have in the interstellar medium in these guys?
That's an interesting question because uh, um, we just had a paper led by Matilde Mingozzi on a galaxy where we discussed JWST mirror spectra of these SPSS 0335 galaxy, which I mentioned before. And there we actually try to explain the mid-infrared neon 5 line, which is a similar problem, right? So it's at 14.3 microns. And so that's actually even worse than, so it's a star-forming galaxy. And the neon 5 line is quite strong there. And for that, you need photons with 97 electron volts. So it's the problem is twice as large. And we discussed the sources of ionization. So stellar radiation doesn't do it. AGN possibly could do it, but there's really no indication that there's an AGN. And also we look into shocks. And shocks actually could not do this. And this was actually very interesting. If you look at shock models, since you have also the precursor shock in the gas, in a shock, typically you have high ionization lines, but at the same time, you also have low ionization lines. So in this particular galaxy, there would be a prediction that there's also strong neon 2, which is not observed. So this is, very often you can actually read in the literature, well, so it could be shocks or so. But once you go through quantitatively through the models, then it doesn't work out because a shock typically has both high ionization and low ionization lines.
Right.
And at least in that galaxy, that was not supported by the data.
Oh, very interesting. Yeah. Very good. Okay, so if there are no other questions, I mean, thanks so much, Klaus. This has been a really nice talk, and all these things are strongly connected with all the beautiful data that we have, like the one you're showing right in front of us. So I think we're very much looking forward to working with Pi Starburst 99. I don't know whether you think of changing the 99 now to, I don't know, 25.
No, I wanted to leave the 99. I like the 99. So
That's good.
we just call it Pi Starburst.
Excellent. All right, Klaus, thanks so much. Thanks, everybody. Yeah.
Okay, thank you.
Thank you. Take care.